Dear students, so today we are going to study the topic of work, power and energy. So today is our lecture number 1 on this topic. So first let us define work. How can we define work? So work has different meanings in different subjects. For example, if you take biology, so here we can say if energy is spent, then we can say work is done according to the concept of biology. So according to biology, thinking is a work, fascination is a work. So anything dreaming is also a work, digestion is also a work, respiration is also a work, and all the chemical changes which are happening in the body is also work according to biological sciences. If you take a chemistry, so in chemistry we can say if any reaction happens, then work is said to be done. So products, reactants are reacting to give some products, then work is said to be done according to chemistry. But in physics we have a special meaning of work done. Work is said to be done only if a force is able to displace a body. So definitely there must be some force, and this force must be able to displace a body, then only work is said to be done. So we are applying force, body is not moving, then we say work done is 0. Body is moving but we are not applying any external force, then also work is said to be 0 in this condition. So for example, we have already studied the equation of work here. So work done is equals to Fs cos theta. So this is the basic formula for work done. So where F represents the external force which we are applying, S displacement of the body, and theta is the angle between this force and displacement. So therefore I can say that if a force becomes 0, then total work done will become 0. If displacement becomes 0, then also total work done will become 0. Similarly, if theta value becomes 90 degrees, then also I can say work done becomes 0 because cos 90 is 0. Similarly, if the same equation, if I want to write in the form of dot product, then how can I write? I can write W is equals to F dash dot S dash. So we know that force and displacement are vector quantities. So if I do the dot product of two vectors, resultant should be a scalar. So definitely you can say work done in this condition is scalar. So F dash dot S dash is equals to W. And if I want to write in scalar form, already we have written Fs cos theta. So for example, this is a body of mass m, and we are applying force in this direction, and displacement also is in the same direction. So here I can say work done is equals to F into S. So directly I can write this relation. So work done is equals to force into displacement. Okay. So instead of like this, if I draw a diagram like this, so force is applied at an angle of theta, and displacement is in this direction. So this angle is theta. Now this is the equation which we can use here. W is equals to Fs cos theta. So same W is equals to Fs cos theta I can write in two forms. Either I can write F into S cos theta, or I can write F cos theta into S also. So like this also I can write. So let us see what is the meaning of this one. So this F into S cos theta represents S cos theta is the component of displacement in the direction of force. Similarly, if I can write in the form of F cos theta into S, it means that there is one component of force in the direction of displacement. So whatever it may be, we are trying to take both the force and displacement in the same direction. Then we are able to calculate the work done in this condition. So let us see what is the meaning of the data which we have written there. So for example, this is the body, force we are applying in this direction, and this is the displacement, this is angle theta. So this force, already we have studied triangle of addition or splitting a vectors into two components. So if this is theta, I can say this is f cos theta and this becomes f sin theta. So f cos theta is the component of vector which is present in the direction of displacement. So therefore, if I multiply f cos theta into the displacement, that will give the work done. Similarly, instead of splitting this force into two components, this displacement vector also I can split into two components like this. So this is also theta, this is displacement, this is s cos theta, and this becomes f s sin theta. Yes, sin theta. So again here force and s cos theta are in the same direction. So here I can write work done is equals to f cos theta into s. And here also I can write work done is equals to f into s cos theta. So if you observe carefully here, we can say that I am trying to take force and displacement, both of them in the same direction. So here also f cos theta and displacement are in same direction. Here also s cos theta and force are in the same direction. So this is how we can derive the equation for work done. Okay. So after this, so let us see the types of works which we have. So types of works we can divide into positive work. Second one is zero work. And the third one I can write it as negative work. So let us see in which conditions I can say work done is positive, in which condition work done is negative, and in which condition work done is positive. So or 0. So for example, if a force is applied in this direction and body is displacing in this direction. So here there is angle theta. So this force, if I can split into two components, this is f cos theta and this is f sin theta. So this f cos theta is in the direction of displacement only. So if there is any component in the direction of displacement, then this type of work I can call it as positive work. So here f cos theta is in the direction of displacement itself. So here I can say this work done is positive. So if I take some more examples, so force is in this direction, displacement is in this direction, this is angle 37 degrees. Then this force I can split like this. So this becomes f cos 37 and this becomes f sin 37. So work done will become f cos 37 into s. So fs into cos 37 value is 4 by 5. So here work done will be, let it be W1 is equals to 4 by 5 fs. Okay. Now similarly, if I take one more angle, for example, if I take that this is the body, force is applied like this at an angle of 53 degrees, and this is the direction of displacement of the body. Then this force vector again I can split into two components. So this is angle theta, this is f cos 53 and this is f sin 53. So here work done will become f cos 53 into displacement. So fs into cos 53 value is 3 by 5. So 3 by 5 fs. So let it be work 2. So here I can easily understand that work done W1 is greater than W2. So what is happening in this condition? as I am increasing the angle in which the force is applied, then the work done is continuously decreasing. And this work done and this work done, both of them I can say it is positive work only, because here also there is F cos theta, a component of force in the direction of displacement. Here also there is a component F cos 53 in the direction of displacement. So if there is a force in the direction of displacement of the body, then definitely I can say that that type of work done is positive work. So up to how much angle can I say there will be a component of force in the direction of displacement, and that angle will be exactly equal to 90 degrees. So up to an angle of 90 degrees, so there will be a component of force in the direction of displacement. Now if I take this force is applied at an angle of 90 degrees to the displacement of the body. Now this force vector I cannot split into two rectangular components such that one component is in the direction of displacement. So we have already studied about splitting of a vector into components. So a vector I can always split in this like this. So here angle between the components should be 90 degrees. So therefore I can say this is also angle between the components which is equals to 90 degrees. But this force vector I can never split such that one component is in the direction of displacement. For example, this is the direction of displacement. Then I have to split this force like this. So, but here angle 90 is not formed here. So therefore, this force vector, there cannot be a component in the direction of displacement. So it means that here work done is equal to 0, or according to formula I can write down W is equals to Fs cos 90. So is equal to 0. So this is the only condition in which work done will become 0. So when displacement is in one direction and force is applied in another direction, that is at an angle of 90 degrees, then this force cannot do any work on this body. So that is, if I say that if this body is traveling with a velocity of v, then this force cannot change the velocity of this body. Or I can say speed of this body speed of this body cannot be changed. But this force can change direction of this body. So velocity continuously changes because direction is changing, but I cannot say that speed will change. Speed always remains constant. So whatever it may be, this force is responsible only for changing the direction of the body, which we have already studied in a circular motion. So if direction changes, I cannot say work is done. Work done in this condition will be 0. Similarly, let us see some more conditions in which work done can be 0. So, for example, so this is a vertical wall. So a person is present here and he is pushing this wall with a force of F. So whatever may be the force he can apply, but this wall is never going to move in this condition. So force applied is not equal to 0, but displacement will be definitely equal to 0, and theta value is also 0 in this condition. So definitely I can say that work done will be equal to 0 in this condition. Similarly, for example, if I am tying a mass of m to a string and it is moved in a horizontal circle like this. So it is moving in a horizontal circle and this string is making this bob to move in a circular path here. So this bob is able to move in a horizontal circle because of a force which is called as tension, and this tension will behave like centripetal force in this condition. Clear? So here, wherever we cut this string, we know that this mass will travel with a velocity of v, which is called as tangential velocity of this body. Similarly, if I cut this string here, then this body will travel with a tangential speed of vt if angular velocity of the body is the same. Okay. So everywhere tension and this velocity or displacement of the body are exactly at an angle of 90 degrees. So if I cut a string here, body will tend to move in a straight line. It means displacement direction will be like this. But tension direction is like this. So angle between tension and this displacement values are 90 degrees. Here also it is equal to 90 degrees. It means that this tensional force can never do work on this body. Work done by this tensional force on this body is always equal to 0. Then what is the effect of this tension here? This tension can only change the direction of this body. Speed of the body cannot be changed with the help of this tension. Clear, ma? So therefore I can say that here also work done condition is 0. Similarly, if I take two blocks like this, so here I am applying a force of F, and because of this force the bodies are moving in this direction. So here I can say, if this is a massless string, here tension will be T, here also tension will be T. So now I want to calculate what is work done by this tension on this body and on this body. So I am taking only tensional force into consideration. This force I am not considering here. For example, this body moves by a distance of x, and if this body moves by a distance of x in this condition. So here tension and displacement, both of them are in the same direction. So this is mass number 1, this is mass number 2. So work done on mass number 1 can be written as T into x in this condition. And work done on mass 2 can be written as minus T into x in this condition. Because tension is in one direction, displacement is in opposite direction. Angle between them is equals to 180 degrees. Cos 180 value is minus 1. So minus T into x. And now if I add these forces W1 plus W2, then it should be equal to 0. It means that this tension totally, it cannot do any work on this system. So this is also an example of 0 work. So here I can say that if there is no relative motion between this body and this body, definitely I can say such forces cannot do any work, or the total work done by this type of forces, they become equal to 0. Clear, ma? So these are the conditions in which work done will become 0. Now let us see what is meant by negative work. Negative work. So work done is negative if there is a component of force in the direction opposite to the displacement of the body. So this angle is theta here. So definitely I can say theta is greater than 90 degrees in this condition. So therefore how can I split this force into two components? So this force I can split into two components like this. So this is F, this is 180 minus theta. So I am taking this angle now. If this is theta, this angle will become 180 minus theta. And this becomes F cos 180 minus theta, and this becomes F sin 180 minus theta. So displacement and F cos 180 minus theta are in opposite direction. So definitely I can say work done is equals to F cos 180 minus theta into S. So W is equals to minus Fs. So this is the minus Fs cos theta. So this is the equation for work done. So cos 180 minus theta is minus cos theta. So this is the equation for work done in this condition. So here there is a component of force in the direction opposite to the direction of displacement. Then I can say work done is possible. So therefore if I can say that if theta value lies between 90 and 180, then definitely I can say that work done will be negative. So this is the condition in which work done will become negative. So these are the conditions. Now let us see work done depending on frames of reference, which is also important concept in understanding the nature of work. So work done based on frames of reference. For example, if I draw a diagram like this, so from car a person is standing here, and this car A is traveling with a velocity of v1, and consider this is another car B. From here a person is traveling on car B with a velocity of v2, so let v1 be greater than v2, and these two people are observing a block of mass m which is pushed by a force of F. Okay, so and consider these are frictionless surfaces, so consider friction to be 0 in these conditions. So this person and this person are observing this mass, and consider this person and this person are in straight line with respect to this mass which is being pushed by a force of F here. Then after a time of t, so let us consider initially this distance between these two bodies, so let it be x1. So x1 is the distance between this body and this body, between the mass which we are considering. So both of them are present on the same distance. So if this is x1, I can say this distance is also equals to x1. So here we have considered that velocity of first body is greater than velocity of second body. So after a time of t1, after a time of t, what happens? So let us consider that this body has reached up to here. So this body traveled up to here, and the same force is continuously applied in this condition. So this body has moved by a distance of whatever it may be, we'll take values with reference to these bodies. And in this time, this car A, it traveled up to here. So this is car A which is traveling with a velocity of v1. And in the same time, because velocity of this car B is lesser than velocity of car A, it will travel only up to here. So this is car B which is traveling with a velocity of v2. Okay. Now I will consider this distance between the block which is in motion and car A is x2, and this distance between car B and the block which is in motion, this is x3. So to this observer, can we say what is the displacement the block has moved? So with respect to observer A, the block has moved by a distance of x2 minus x1. And with respect to block B, the person present on car B, that block has moved by a displacement of x3 minus x1. So this will be the displacements. So definitely I can say that because velocity of this person is greater, definitely he will travel a bit greater distance when compared to this person who is present on car B here. So definitely I can say x3 minus x1 must be greater than x2 minus x1. It means that relatively, when compared to this car, to the observer who is present on a car B, that block has moved by a greater distance. So again, if I write work done is equals to force into displacement, then work done according to observer A will be equal to force into x2 minus x1. And with respect to observer B, I can write down work done is equals to force into 2 x3 minus x1. So these are the values how I can write. So definitely I can say that in this condition, this WB must be greater than WA, because x3 minus x1 will be greater than x2 minus x1. So here actually for an observer who is present on the ground, for example, if a person is present on the ground and he is observing this mass of F, then he will see what is the actual displacement of this mass. But these two persons, they will see a different displacement of that massium. Definitely work done with respect to these two cars will be different when compared to work done from the ground reference of reference. So it means that work done always depends on frames of reference also. So definitely these two are traveling with the same velocity here, so they are inertial frames of reference. So work done always depends on inertial frames of reference also. This is a very important point which we have to understand. Okay. So after this, let us study about work done by variable force. So work done by variable force. So if work done is a constant, then I can write W is equals to Fs cos theta. And if force and displacement are in same direction, I can write W is equals to F into S. Just simply I can write like this. So this formula is exactly in the form of area is equals to length into breadth. Area is equals to L into B. So that is, if I take a graph of force and displacement, where force is a constant, and if I consider this area, where initial position is S1, final position is S2, then displacement will become S2 minus S1. Then area under this graph should give the work done. So therefore I can say area under Fs graph gives work done. Okay, because already we have discussed these type of assumptions. So wherever equations are present in the form of area is equals to length into breadth, then area under these two parameters will give the physical quantity which is present on the left side. So here area under force and displacement will give the work done. So in this condition I can say this is equal to positive work, because force is also positive, displacement is also positive. So this type of work I can call it as positive work. Similarly, if this is the force, this is the displacement, and if graph is given like this, then this will become the area under this graph. So here also this area will give the work done. But this work I can say it is equal to negative, or negative work is done here. Why? Because displacement is definitely positive, but force applied is negative. So force is in one direction, displacement is in another direction. So this type of work done I can say it is equal to negative. Similarly, if a graph is given like this, so force and displacement, and graph is given in third quadrant like this, then here also I can say this area will give the work done. But here in this condition, this work done will be positive, because force is also negative and displacement is also negative in this condition. So definitely this type of work done I can say it is equal to negative. So this is a small discussion on area under force and displacement graph. Now the question is, how can we understand when force is variable? So in all these conditions we have been discussing the concept of constant force here, magnitude of force is constant. But if force is applied like this, so let us see. So if I draw a graph between force and displacement, then graph is coming like this. So this is the given graph. So in this condition, how can I calculate the work done? So whatever may be the type of graph, always the area under force and displacement graph will give the work done. Somehow, if I can calculate area under this graph, then definitely this will give the work done. But the question is how to mathematically represent this equation when force is a variable value. So that let us try to understand. Okay. So here this is force and this is displacement, and this is the given graph. So here I will try to split this graph into very small intervals such that for each interval force has almost become equal to constant. Okay. So if I consider this interval like this, one interval, for example, this interval, I am drawing a magnitude view of this one. So each interval is so small that this force appears to be almost constant. So actually it is a slope. It is a continuous curve which is traveling. And for very small displacements, this becomes a straight line. So this is the condition in which I am taking, and this small interval, I can take it as ds. Very small displacement such that force is a constant. Then the very small amount of work done for this small displacement, I can write it as dw is equals to f ds cos theta. I can write like this. So very small amount of work done for a very small displacement is this one, dw is equals to f ds cos theta. So I got equation for only very small amount of displacement here. Then how can I calculate the total amount of work done throughout this interval starting from S1 and ending up to S2? Very simple, you add all these small areas, then I will get the total area, and total area will give the work done. So this addition of all small values is nothing but integration. Already we have studied the concept of integration in the previous classes. So therefore you integrate on both sides. So integration differentiation gets cancelled. So w is equals to integral of f ds cos theta, and f I am integrating with respect to ds here, and the limits of ds are from s1 to s2. So this becomes my equation for work done for the case of variable force. So w is equals to integration of f ds cos theta, limits are applied from s1 to s2. Or same equation I can write like this also in the form of vectors. So s1 to s2, f into or f dash dot ds dash, I can write like this. So this is the equation in which I can write for work done under variable forces. Okay. So let us do a small problem based on this variable force. For example, a force is acting along x-axis according to the relation f is equals to 3x square plus 2x plus 1. Calculate the work done between the intervals x is equal to 1 to x is equals to 2 meters. Force is given in newtons. So this is the given question. So clearly here I can say that this force is changing according to x value. So if x displacement along x-axis is increasing, force is also increasing, and I want to calculate the work done in the intervals of x is equal to 1 to x is equal to 2 meters. Then I can use the condition of variable force here. So w is equals to integration of s1 to s2 f dash dot ds dash. So force and displacement, both of them are in the same direction. So I can write s1 to s2 f ds cos 0. Cos 0 value is 1 here. So integration of limits of displacement are from 1 to 2. And force equation is 3x square plus 2x plus 1 into dx. So W is equals to, now if I integrate this one, 3x cube divided by 3 plus 2x square divided by 2 plus x, and the limits are applied from 1 to 2 here. So if I can solve this equation, then W is equals to x cube plus x square plus x, and the limits are applied from 1 to 2 here. So W is equals to 2 cube plus 2 square plus 2 minus of 1 plus 1 plus 1. So W is equals to 8 plus 4 plus 2 minus 3. So W is equals to 10. 14 minus 3 is equals to 11 joules of work is done in this condition. So this is how I can do the problems when force is a variable value. Okay. So work done by static friction. So let us take some example of this one and try to understand the meaning of this one. So for example, this is a body of mass m and we are applying force in this direction, and the body is not moving here. If body is not moving, it means that an equal and opposite static friction has developed in opposite direction. So what is the work done by static friction in this condition? I can say that work done by external force is also 0. Similarly, work done by static friction is also 0 in this condition because body is not moving. So definitely I can say work done by static friction will be always 0 on the or on both the surfaces, or on both the surfaces. This is how I can write. Okay. So work done by static friction will be 0 on both the surfaces because this friction is definitely present but bodies are not displacing. So when bodies are not displacing, definitely I can say work done is 0. That is the actual definition of work done, which we have already discussed. Now based on this condition, let us try to calculate a condition of one block placed over the other block. For example, this is a body of capital M and this is a block of small m, and here I am applying a force of F. Consider this is a smooth surface, and here coefficient of friction of mu is present. That means friction is present. Friction can be present between small m and capital M, but there is no friction between capital M and the ground. Now if blocks are not sliding, so here it is given that these blocks are not sliding with respect to each other. Blocks are not sliding with respect to each other. Then calculate work done by static friction on small m. Similarly, calculate work done on static friction, work done by static friction or capital M, and calculate the total work done. This is the given question which we are supposed to find out. Clear, ma? So if I apply force like this, definitely this capital M starts movement on this surface because this is a smooth surface. And the value of F is such that there is no relative motion between small m and then capital M. Okay, now let us see. So as both these blocks are moving like a single block, definitely I can use the Newton's second law, F is equals to ma. So A is equals to F by m. Force applied is F and total masses are present are m plus m. So therefore acceleration produced in the system or acceleration of both the bodies is A is equals to F by m plus m. Okay. Now if I take this small m, question is, in this small m an acceleration of A is equals to F by m plus m is produced. So if acceleration should be produced, definitely there must be some force, but force is not acting on this small m force is acting on capital M. Now the question is, who is giving this acceleration to small m? So definitely I should say that the static friction which is present in this capital M and small m, that is responsible for providing acceleration to small m. And as this m is moving in this direction, definitely I can say this must be the direction of static friction. And this is the only force which is acting on this small m when you neglect weight and normal reaction. So this Fs will become the net force acting on small m. And we know that F net is equals to MA, and which is equals to Fs. Okay. So therefore, if I write this relation, then Fs should be equal to m into acceleration value already we have calculated, which is equals to F by m plus m. So therefore, I have calculated what is the force which is acting on small m. Now I want to calculate work done, and to calculate work done I require force and displacement. Force I have already calculated, then how can I calculate displacement? So displacement I can calculate by using S is equals to ut plus half at square. So actually we are calculating work done after a time of t. After a time of t. Okay. And these blocks, they are starting from rest position, initial velocity is 0. So therefore I can write S is equals to 0 plus half at square. So S is equals to half into acceleration equation already we have calculated, F divided by m plus m into t square. So therefore total work done is equals to force into displacement. Force equation already we have written, m into F by m plus m into displacement equation is half into F by m plus m into t square. So therefore that should be the work done on small m by the static friction. So therefore work done on small m by static friction is equals to, so I can multiply those values, Fs square t square divided by m plus m into whole square into 2. So this is the amount of work done. Similarly, I want to calculate what is the work done on capital M. So this, how can I calculate? So already we have studied that work done by static friction on both the surfaces combinedly, it will be equal to 0. So therefore I can say work done by static friction on small m plus work done by static friction on capital M. If I add these two, they should be equal to 0, because relatively capital M and small m, they are not moving. So static friction cannot do any work on these two bodies as they are not in movement relatively. Clear? So therefore work done on capital M should be equal to minus of work done on small m. So minus of work done on small m already we have calculated, Fs square t square divided by 2 into m plus m whole square. So this much amount of work done is amount of work is done on capital M with the help of static friction. Now total work done already we have written equation here. Total work done on small m and capital M due to static friction should be equal to 0. Okay. So this is our small discussion on work done.